Today I would like to talk to you about the Penn State in-service workshops in astronomy. These are annual week-long summer workshops that we teach at Penn State that help high school teachers educate their thousands of students better about topics such as black holes, cosmology, stars, and the scientific method. And these workshops have a 25 plus year history of success here at Penn State University. Today I'd like to tell you about the audience for these workshops. Here pictured is the 2023 workshop attendees. I'll tell you about how we teach the workshops, about how we assess the workshops and follow up on them, and then I'll end with some broader lessons learned about from teaching these workshops. Here are the two most recent workshops that we've taught on the lives and deaths of stars and black holes. These are advertising flyers for the workshops. You can email me if you have interest in being added to the distribution list for the workshops. In terms of the audience served, well, ultimately, we are aiming to improve student astronomy education in Pennsylvania, which is a large U.S. state, has about 13 million people, and Pennsylvania's neighboring states. Our overall approach is to teach the teachers, which is a high leverage approach, because each one of these teachers will go on to teach many hundreds or thousands of students in the coming years. Annually, about 12 to 18 teachers attend our workshops, and we make special effort to recruit teachers from underserved rural and urban school districts. They are supported with NSF scholarships, which cover travel, lodging, meals, and so on. And then the teachers also receive continuing education credit for the workshops. That requires workshop accreditation, but it's very valuable and helpful for the attending teachers. In terms of the instructors, well, in recent years, the main workshop instructors have been myself. I'm a professor at Penn State. Chris Palma, pictured here, who is a Penn State teaching professor and an author of astronomy education research articles. Glenn Goldsboro, pictured here, who is a master teacher of physics and astronomy at Pennsbury High School. He brings a critical perspective in making this the material we teach actually useful to the high school teachers. And the way things break down is generally I lead content lectures, and then Palma and Goldsboro lead hands-on activities and discussions on pedagogy and curriculum, and also lead nighttime observing and so on. In addition to the main instructors, well, the Penn State Department of Astronomy and Astrophysics, one of the largest USA astronomy departments, provides additional guest lecturers. And here pictured are three guest lecturers from our 2024 workshop on black holes. And these included postdoctoral scholars and professors who brought in their expertise and covered a number of other very interesting topics of importance to the workshops. In terms of standards, well, the workshop content, we put a lot of effort into aligning this with the next generation science standards and with the Pennsylvania so-called STEELS standards, which stands for the Science, Technology, and Engineering and Environmental Literacy and Sustainability standards. And in addition to sort of making sure we check the boxes in terms of content coverage with these standards, we also put in significant effort to illustrate effective applications of the scientific method, and we aim to show how science research actually gets done, and we have our department right around us, and so the teachers can witness a lot of scientific research getting done around them. So that's very important part of the workshop also. And just to sort of be a little more specific, I want to just highlight the black holes workshop that, again, we taught last summer. There were a number of content presentations. I taught these in general. I started off talking about Schwarzschild solution for black holes. I then talked about stellar fates and black hole formation. And then I talked about observations of black holes, both stellar mass black holes in our own galaxy, and then supermassive black holes, both in our galaxy and then in active galaxies, and then hibernating in other galaxies. And then after covering all that material, I moved on and talked about some selected topics of interest: spinning black holes, the no-hair theorem, black hole evaporation, singularities, and what goes on inside black holes, and so on. So those were the main topics covered. The teachers asked many questions about these topics as we went through them, so there was a lot of valuable back and forth, which enriched the whole experience for the teachers. In addition, of course, to this content presentations, of course, these activities that I've mentioned, again, led by Chris Palma and Glenn Goldsborough, are critical for the success of the workshops. There were activities on modeling black holes in the classroom, investigating stellar density and the compression of a star down to make a black hole with compressing down tinfoil balls. There were coverage of resources and activities to teach stellar evolution. There were also tutorials on finding black holes in binary systems. There was a review of planetarium resources on black holes. There was also connections with the Sloan Digital Sky Survey. Here are the teachers holding their Sloan Digital Sky Survey plates that they learned all about, and they brought these back to their classrooms to teach their students about the Sloan Digital Sky Survey, also Rubin Observatory and other modern surveys. And then, of course, there's also rooftop observing. Here's an image of the teachers, I believe, observing the sun on the Davy Lab roof. And then here is a nice activity that is done where Chris and Glenn put heavy weights on a stretchable cloth to sort of give the teachers a visual understanding of the curvature of space-time close to a black hole. So there's a number of critical activities which help to make the workshop successful. In terms of assessment and follow-up, well, number of points there. Well, after years of iterative improvements, the workshops now receive excellent formative and summative evaluation scores and comments. The attendees especially appreciate, according to their comments, the comprehensive and in-depth coverage that the workshops are able to provide. And the workshops have also been positively reviewed over the years by the Penn State Center for Science in the Schools, an independent center at Penn State, and also the Pennsylvania Space Grant Consortium. And after the workshops are completed, we strive to maintain contact with the teachers via social media groups and email so that we can help them if they need help putting out, preparing lesson plans and so on, and making sure the material gets out to their students. And it's gratifying to see that the workshops have indeed helped the attending teachers confidently teach astronomy concepts and prepare relevant lesson plans. And then, more broadly, in terms of lessons learned for the workshops, well, the workshops clearly are hard work, but they are highly rewarding. And iterative improvement year over year is critical. You won't get everything right the first year, but if you keep improving them, after a couple years, they can get to be very good. I found that year one of a new workshop is especially tough. It's like teaching a new classroom course, but without much of the standard university support framework, because these are often done outside the normal university curriculum. So there's a fair amount of bureaucracy that has to be done, in addition to all the classroom preparation work to make the workshop successful. It is also good to cross-pollinate the workshop material with one of your standard classroom courses. I teach a course on black holes for our undergraduates, and I can use that material to improve the workshops, and then take the workshops and use them to improve my classroom teaching and so on. That's also very valuable. And then, well, for long-term success, I believe you may need to plan ultimately to develop content for 2 to 4 workshops. Otherwise, the teachers who have interest tend to saturate, and the attendance can drop off. But if you have a variety of workshops, you can keep things vital and interesting for the teachers. And then it is also extremely helpful, as I've mentioned, to team up with education experts and a high school teacher. They give extremely valuable perspective, especially getting the direct inputs from a high school teacher as to, well, this approach will work and this approach will not work. That can help you avoid a lot of pitfalls. And then, of course, it takes an engaged department to sustain a workshop program more generally, at least in my experience. And so, reaching out to your colleagues in the department and your department head and getting them involved in the workshop can be extremely valuable as well. And then just to end, I would like to thank our sources of support, the National Science Foundation, the Penn State Eberly College of Science, specifically our Department of Astronomy and Astrophysics, and also the Penn State Bookstore through Barnes & Noble. Thank you.
Hi, my name is Jackie Bondell. I'm the Senior Education and Outreach Manager for the ARC Center of Excellence for Dark Matter Particle Physics based in Melbourne, Australia. And this talk is called Bridging Scientists and Students with Regional School Partnerships. So just to give a little bit of background, so I work in this role as a senior education and outreach manager for this group, as well as a gravitational waves research collaborative. And my job is to take the contemporary research that's happening and connect that with students, teachers, and the general public. I also serve as the Australian representative to the International Particle Physics Outreach Group, as an EPO committee member for the LIGO-Virgo-CAGRA collaboration, as well as a NIAC for the IAU for Australia. And my email's there if you want to reach out to me about this project. It's jackie.bondell@unimelb.edu.au. And my background, I was academic, then I switched into education, spent a lot of time doing physics teaching and curriculum design, and now I get to work in a space where I get to bridge the science and the education. So just a little background and context. So I said this term, an ARC Center of Excellence. What it is, it's an Australian funding program where it's a multi-university research collaborative that has a funding from the government for 7 years to build easier pathways for collaborations by having researchers working in areas with a common theme driving ambitious science. So for the Dark Matter Center, as we call it for short, one of our major projects is the Southern Hemisphere's first underground physics lab, which is in rural, or what we call regional, Victoria. And it also includes some funding for outreach, communications, education, and EDI initiatives. So in the education and outreach portfolio, the main goals are to try to increase uptake and access to STEM opportunities for traditionally underserved groups. And we want to incorporate regional science connection in Stawell, Victoria, which is where our lab is. We want to develop programs and resources to support educators and to build the science communication capacity of our center members, especially our early career researchers. And today, I'm going to focus specifically on a project which is directed to increase this uptake and access to STEM opportunities in specifically our regional locations, as well as you can see how this program supports, also leads to providing support for educators. Now, you've probably seen this before. I enjoy this quote from the A Bridge Beyond the Point of Usefulness science book. And it says, Aristotle said a bunch of stuff that was wrong. Galileo and Newton fixed things up. Then Einstein broke everything again. Now we've basically got it all worked out except for pretty much everything. And I like to highlight this because if you look at the what's called the VCE Physics Study Design. So that's just the state level Victorian curriculum authorities year 11 and 12 physics program, physics study guide. And one of the things that I think is relevant here is that, yes, we want to teach about how we do science, develop those skills. But I think one of the key things in the second paragraph is increase our understanding of the scientific processes, insights into how knowledge in physics has changed and continues to change in response to new evidence, discoveries, and thinking. And I think this is where dark matter science really plays a role. So I'm going to talk about something called the Dark Matter Partner Schools program. And for this program, the goal has been, since the start of the center, to create a program in which we can have a high impact long-term engagement with partner schools, where these partner schools are in regional locations. And we want this program to be relevant. We want to have a measurable impact, and we want it to be longitudinal in the fact that, instead of having one-off programs with many schools over the 7-year lifespan, what we're trying to do is to create, see if we can have an impact by focusing our energy on creating relationships with schools and students and see if that longer term engagement has an impact. And we specifically want to leverage partnerships. So we started this program in that same small town where our underground physics lab is at the bottom of the local gold mine. And in addition, we are creating content for teachers. We're trying to, once again, help our center scientists engage with students, and we want to measure the impact. So our dark matter school program, we've got 7 schools in very regional areas. We're currently on our 4th year with the first school that we piloted this with in Stall, Victoria. We take a scaffolded approach so that what we do one year builds on what the students do the following year, with an emphasis on the nature of science. So not necessarily all dark matter content, but using dark matter as the lens through which we can understand the nature of science and the evolution of scientific understanding. Additionally, we are offering extended investigation projects for these students that they wouldn't otherwise have access to. And we're working with the University of Melbourne's Faculty of Education to look at the impact of the project. So next, I'm just going to focus on these 3 things in a little bit more detail. Now, the structure, like I said, is scaffolded. So obviously it's curriculum aligned, and we start with students in their first year of secondary school. Secondary school in Australia starts in year 7. So that would be equivalent to 7th grade in the US, where students are about 12 or 13 years old. And usually they will do common curriculum, covering very broad areas, year 7 through 9, some schools through year 10, and then for years 11 and 12, their last 2 years, they get to focus on a few specific areas. So in year 7, we start with this activity. How do we learn about things that we can't see? We talk about yes, we use dark matter as a lens, but really focusing on how we can learn about things that we can't see using traditional methods, and really getting into that scientific inquiry. In year 8, to align with their study of gravity, we talk a little bit about, and forces, we talk a little bit about how does gravity provide evidence for dark matter. So we talk about the solar system and how things move and how gravity impacts the motion of objects in a fairly qualitative manner. And then contrast that with what we see in galaxies to say, hey, this provides some evidence that there could be something that we don't quite understand yet. Year 9, we get a little bit more into how do we use light and how do we use that to map dark matter. Year 10, we start talking a little bit more about the structure of matter. So, atoms and how, what normal matter looks like, and contrast this to what dark matter may be. And then finally in physics, it opens up a little bit, and we're able to work with students discussing standard model, muons and special relativity, laws of gravitation, and all of those. So again, a strong focus on the nature of science and scientific inquiry with the context of dark matter. We also are providing extended investigation projects for our partner schools. So these are research opportunities for the upper level regional high school students to work with center scientists on year-long projects. We've done a strong push on the incorporation of muon detectors because that's been one of the areas of research for our scientists, focusing on the muon detection for our underground lab. And additionally, we're working on projects to collaborate with students in the US on high altitude muon study projects over multiple years. Last but not least, in the last minute here, I just want to talk a little bit about some of the early stuff from our collaboration by looking at the educational impact of this. So we wanted to look at what the impact might be by targeting these traditionally underserved schools. And with the university researchers from the Faculty of Education have done data collection through surveys, focus group, and interviews with teachers, students, and administrators. And the early data is showing that there seems to be a positive impact on the students' sense of belonging in science. And, that's an important indicator of whether they will uptake it in the future. And there also is sort of this unexpected thread of a pride and a sense of place in the locality of the experiment, and students really identifying with that science happening in their region. So this is about all I have time for. I will leave you with this final slide about one of our additional programs in which we travel around Australia, going to very remote schools as part of National Science Week initiative. Thank you.
Hello everyone, my name is Melissa Solares. I'm the National Astronomy Education Coordinator in Guatemala, and today I'm going to be talking about my experience in creating and implementing a course for astronomy as its own subject in high school. Thank you for joining the talk, and feel free to contact me at any point. I'm giving my contact information at the end of the presentation if you need help or insights or anything, or even if you have some recommendations yourself. So I'm going to be talking about 4 main points. The first one is how to get started, how to set that foundation for your astronomy course if you're interested in doing something similar. I'm going to talk about the first steps and the trial runs that I did during the first years that the course was implemented. Then I'm going to talk about the strategies and give some examples of how I engage my Gen Z teenagers in science. And the last topic I'm going to cover is extracurricular activities and STAR pupils and how to provide opportunities outside the course. So how to get started, how do you get your course running, how do you build this course from scratch? So in Guatemala, I do need to give this background information. In Guatemala, there are no schools that teach astronomy as its own course. The national curriculum does not include astronomy as its own course as well, and the little contents that are taught are just about the sun, earth, moon system, and they mention the planets, but that's pretty much it. So I'm going to tell you how to build it from scratch, how to build it in a nutshell. The first thing that you need to do is, of course, get yourself the initial knowledge through diplomas, get some information about the theoretical framework that you're going to build your course on. So there's open education courses, you can do self-study, mentorships have been something that have helped me, of course. I have my college professor that taught me astronomy for the first time. He was a complete inspiration, and the course I built later on was based on how I was taught astronomy by him. So basically, be a student before teaching your students. How did I accomplish this? I took astronomy courses in college. I got a teaching degree in teaching math and physics, and in the combination of all of this, I later on went back to college and got an astronomy diploma. So it's basically just getting all of this background info first. After that, something that helped me greatly was taking ideas from other existing curricula around the world. So studying other teachers, other courses that have already been built, are already running, and documenting all of these findings, trying to find connections, and asking for expert revisions helps so much. Peer evaluation is a key part in building this course and making sure it's going to be successful. So I did this actually as part of my dissertation, my bachelor's dissertation. So the first step I did was a phenomenological research in which I gave talks to high school students, and I documented their reactions during these talks, and the talks were based on mathematics, physics, and astronomy. So the idea was trying to document that there is a preference towards astronomical topics in comparison to other sciences. So trying to find that point in which you demonstrate the relevance of what you're doing of your work. And then I later on did a state of the art in which I documented all of the curricula from other places in Latin America, and I took this curricula and I modified it a bit. I made my own course, and then I later on sent it to these experts. I found online. I can definitely give you the names if you contact me afterwards. And the experts revised my curriculum and they made some adjustments, and that's the final one I'm already doing. So this is the third step when you adapt and create your course. So your expertise and knowledge is the most valuable tool in the artistic process of creating the curriculum. I recommend setting high standards for your students, assess them, and then later on adapt them. So it's a really exciting and ongoing process. This is where you get to put your own personal touch in the course that you're building. And then the final course that I built consists of 5 units of content, which I'm going to show you right now. This is what my course currently looks like. It's taught as an elective course in high school. You can see the units right here. We start with the introduction to astronomy. There is a brief history of the universe and universal motion. So we talk about the universal law of gravitation. Then we talk about the Earth being part of the solar system, matter, light, energy. And then we finally end the course with stars, galaxy, and interstellar phenomena. So it's an extensive course. It's meant to last a year long, and it's a high school elective, so students from grades 11 and 12 can take the course. If you need more information on this, I'd be happy to help you out, and you can just write. So the first steps and the trial runs that I did happened during 2018. That's the first year I implemented the course for. So basically, education is responding to society, and the society is ever changing. So your course also has to be adapting through the ages. In the beginning, I had a highly conceptual course. Very little hands-on activities, and I also had difficulty engaging and keeping Squirmy students engaged. So this was later on changed during 2020 and 2022. So I had larger groups of students. They were older students, and this is when I started implementing hands-on activities, inquiry-based and research-driven high school classes. It was during the pandemic, so classes were virtual and hybrid, and I focused mostly on individual learning strategies because everybody was at home learning. And then I finally found success when we implemented summative group projects. So this were kind of like my initial experience, things I did, things that didn't really work out. And then to the present day, I have about 120 students that sign up for astronomy every year. There are 5 sections running. So there's a new teacher that is helping me out. The teacher also went through training. She went back to college. She took an astronomy diploma, and now we have about 25 students per class. This year, students liked the course so much that they asked for a continuation of the course by teaching astrophysics. So this year we implemented astrophysics. And then there's students that are also choosing astrophysics and aerospace engineering careers as their college majors. So astronomy education is relevant. Students love it, and it's kind of giving that opportunity for students who are already interested in the science and they don't know where to start. So this is a starting point, and you can see some of my students that have gone on to college to study space-related careers afterwards. So what strategies do I use? How do I engage my Gen Z teenagers in science? There are several educational and pedagogical models. I focus mostly on universal design for learning applied to astronomy. So this design, it's an extensive framework, and it mostly has 3 branches, which is providing the students with multiple means of engagement, representation, and action and expression. How does this look like for astronomy? First, for engagement, I have several strategies that you see here. I'm going to go through them a bit fast because of time. So specifically, theoretical classes with note-taking templates, something like this. I also have jigsaw-like reading guides, which is when I take this big document, I break it down into activities in groups, and then they do a discussion all together where they share what they learned from their reading guides, but with different activities, so like podcasts, models, role plays, and everybody gets together in class. I do, of course, Edpuzzle, Nearpods, Quizlets, and I find that models are something that students, high school students, really love engaging in. So having that hands-on, creating things that look like what they're seeing in space is something that they love. So they do constellations, they do sundials. This is actually a model of a constellation in which, if you see it in depth, the distance from the little light bulbs towards the observer are to scale with the distance in light years from the stars to the Earth. It's a model of Draco, and you can see the deep space objects there. So we have all of these educational activities that you can apply with your students, and they can work wonderfully. If you want to try solar systems to scales, is another one that they also love. When it comes to representation, we use vocabulary slides, flashcards, articles, podcasts, and then students researching using AI tools, of course, and then also completing CR charts with the use of simulations. So this is a simulation I love. It's called Star in a Box, and it's wonderful. In case you haven't tried it out yet, you can write to me and I'd be happy to send you the link. And the last one we have is multiple means of action and expression, and this is my favorite one because it's when you get to assess the students in different ways than your conventional test. So I normally perform interviews as a way of assessment. It's normally an open interview, and it's just picking students' brains out and seeing how much they learned about a certain topic. They also communicate astronomical information or news through social media. So this is something that has worked wonderfully. They're great at making TikToks. They create Instagram pages where they are communicating true scientific knowledge, debunking some misconceptions. Students also love teaching students from lower grades. So sometimes I have them do little comic books, and then they do read out louds to students from pre-K or first grade. So they're teaching them about eclipses, the moon phases, and basic phenomena. So in this teaching moment, you can assess wonderfully, and you give them the opportunity to share their knowledge with others. This works amazingly. And you can see them doing the read out loud here. And this is another view of the comic book that my students can make. They also make memes to communicate astronomical knowledge. And lastly, they can also create board games. This is one of my favorite strategies, using board games to represent the stellar cycle. So during the board game, they're asking questions about the HR diagram, about the life cycle of a star, the elements that are being burned, the temperature, etc., etc. Board games work amazingly. And the last thing I'm going to talk about is the extracurricular activities and the START pupils. So it's basically providing opportunities and extracurricular activities as bridges to space sciences. It's opportunities for students who can't really take the course yet because they haven't reached the age level. So astronomy clubs are an amazing starting point. I enlisted here some of the international and national contests that we do here. We have National Astronomy Olympiads. We have the Latin American Astronomy Olympiad. So it's after school activities that you can also inspire your students in joining. And then lastly, they can go to conferences and college level talks. If you can organize field trips to those things, it inspires students. The most important message here is for you to listen to the students and let them inspire you back. So I have a picture here where you can see one of my students. She is co-writing a book on observational astronomy in Guatemala. This is an after-school activity that she does by herself, and I'm of course revising everything and helping her with feedback. But it's these types of activities, this type of extra support that you provide to them after school that really gets them going. So I have one last thing to comment on, and it's that every step we take towards including astronomy education counts. Every little astronomical example or analogy we include in our practice, even if we're not yet teaching astronomy, that counts. Every small talk we have with the students after class, every question we decide to respond to instead of dismissing. And then every student we inspire to follow their passion and to teach them that there is a field of work in astronomy and space sciences. So what we do today counts. So why not start now? Thank you so much. I am giving you my information here in case you're interested in contacting me. I'd be happy to help you in anything you need. And I also am happy to receive any help that you have from your personal experiences around the world. Thank you.
Hi, thanks for joining me. My name is Heidi Schran, and I teach secondary school science at Talawanda High School in Oxford, Ohio, in the USA. And I'd like to share with you an amazing opportunity I had last April with doing some authentic research with my astronomy students. Actually was all of last year. So who we were a group of 9 students, 2 of them college students, 7 secondary high school students, age range 15 to 19. And then there I am second to the right, and Joanna Hone was the STEM outreach coordinator for Miami University of Ohio on the far right. And Joanna had found the grant opportunity and suggested that I apply for it. And she was like my SAG help throughout the process. And then we are located in Oxford, Ohio. There is a picture of the US map. Ohio's in the eastern side of the middle. And Oxford is the far bottom left town on that picture in the center. The 2 blue lines are the path of totality. And where we got to experience 2 minutes and 53 seconds of totality last April. It was amazing. So where did the money come from? Well, Cosmic Pictures is an IMAX group. They make documentaries in the IMAX format, and they got a National Science Foundation grant to pay for a lot of different things, in part our research and our training of our students. The money went to both the National Girls Collaborative Project, which it helps to further young women in their skill sets and in STEM and out of STEM. And then the Dynamic Eclipse Broadcast Initiative at Southern Illinois University. They did all things technical with getting the equipment, training folks with the equipment, getting the programs to take and process the data. And they have already run in 2017 a citizen science research initiative just like this one. And they had a total of 80 teams, 20 of which were part of the grant that I got to be part of. And we, at the bottom there, you see us all in Cleveland. There were 20 team leaders met in Cleveland in November, and we got trained on the equipment. And there we are again. And on the right, you see our equipment. It's a digital telescope, so there's no eyepiece, but the red hexagon at the bottom there connects directly. It's a camera directly up to a laptop they provided with us. And they provided the mount, the tripod, the programs on the computers and everything. Then they trained us on that. And as a novice, I went back and my goal was to train the students on my team, collect a team and train them by April on how to run it on their own. So we practiced through the winter. A lot of times we had to practice inside my classroom and during and after school because it was too cold outside to practice. But some of the time we were able to go outside when it wasn't too frigid and set up the equipment. And you can see us on the right there, all bundled up. It was probably mid-February. And we would not just have single practices on our own, but would also connect up with our the total of 20 groups would connect up at the same time. And folks would communicate through Discord, which was a learning curve for all of us, and get us to all practice as if it was Eclipse Day and we're all doing it at the same time. And that helped the folks at Southern Illinois University to rehearse their job as well, collecting all that data at once. And those are some of the images our team took during our practice sessions. As we got closer to the eclipse, there was a lot of media coverage, and that gave my students a chance to practice their public speaking skills and to share their knowledge and even cement it more and master it more by having to share it. And it got to be, we had multiple newspaper interviews and at least 5 different television interviews coming up right before the eclipse. We did some outreach events as well. We had a eclipse program at our local library, and some of my students went to a local elementary school to share how to watch the eclipse safely with second graders. And then the weekend before the eclipse, our town had a celebration of the eclipse up in the center of town. And we brought our telescope up and set up ways to watch the eclipse safely. My students helped community members build pinhole viewers. And we had the one last really good practice before the eclipse. And so we had the telescope there and could share with the community that stopped by some of the images that we were collecting of the sun that day. So on eclipse day, we all got to the high school, which was our place of practice and our place for the eclipse day. It was away from crowds. There was no school that day. It was canceled so that students could be at home watching the eclipse. But my team came to school and worked longer than a school day on the eclipse. And we also had a watch party, so we invited family and friends, but we knew that they would allow us to get our work done. But we did have lots of folks come by and ask us questions that were in the area. So before and after totality, our students had the job of running the partial programs. Partially eclipsed was where it gets its name, but it would take multiple images every minute and then get rid of any errors in the images and make a really crisp image every minute during from first contact up to totality, and then after totality to last contact. During totality, or right before, they had to cover the lens of the telescope and remove the solar filter, and then start a whole nother program. And then when it was time, allow that program to capture the sun during totality. And this program collected images at 4 different exposures, rapid fire right through. And when we first ran it, we thought something was wrong with the program because the screen would get super bright. And they're like, that's what's supposed to happen. We're like, okay. And then when we're all said and done after the day and the eclipse was all over, we still had 2 more programs to run. And those were to get rid of any artifacts that were on the lens or in the program or in the camera. Sometime in March, we were offered the opportunity to live stream video of the images we were getting that day. And our team said yes. And so I had 2 students just take the reins on this. They set up the equipment when we first got it and took it out of the case and figured it out, made their own labeling system with different symbols and instruction sheets, and it was just amazing. That's them there setting up the streaming site, and I had all different programs and different equipment that the group had to get comfortable with, and they just mastered it and were great. And then other team members spent the day, we called it babysitting the telescope. They watched to make sure that the image didn't drift out of view and that it didn't get out of focus. As it heats up or cools down, the lenses can change shape and get out of it can get slightly out of focus. Make sure the exposure was correct and that they were running the correct programs and all of that. And on top of that, they continued to educate. That's a picture of our watch party there, and on the right you have one of my students sharing with my grandson how you can use a colander to look at the sun before the totality safely. One of the main goals that I had to share with my students was the joy of doing science research, and it was a huge commitment for them. They are at school from 7:30 in the morning till 3 o'clock in the afternoon, and then many of them have sports or activities or in multiple sports or activities afterwards. Some of them were doing college visits at this time as in that spring. Some of them were gearing up and took the ACTs just before this. So they were very busy students and put a lot of time to learning and mastering and being comfortable with the equipment outside of the school day on their weekends. And then there was a lot of things that were out of our control, such as the weather. There's a screenshot of the weather app for today would have been April 8th, the day of the eclipse. And every day afterwards was raining, but that day was sunny and 76 Fahrenheit, which in Oxford, Ohio, on early April is a very rare thing. And the newspaper had the weekend before forecast of snow over the weekend. So it was just an amazing stroke of luck that we got to have the weather that we did. And this picture is something I wanted to share with you all. Joanna Hone, the woman from Miami University, captured it and shared it with me. If you zoom in on my students, they are just elated and having a great time while in the middle of or towards the end of their long workday. And then there's one of my students who's focused in, she's locked in, she's got the screen and she's doing her job, and you can see on the screen that it's just a sliver of the sun left right before totality. And on the right, that's me. And I was just so excited and so just delighted that everything had gone so well that I was hopping up and down. I was so excited. And I was so glad that Joanna had captured this picture, because I don't know if I would have remembered that I did that. After the eclipse, we had a data party. And during the data party, I shared some of the data that we had. And the students got to look at the images. We shared pizza. We got to chat a little bit about some of the fun things that were coming up throughout the rest of the year, that they could join me with the telescope and still get to use it and have fun. And then Alice and Alan from the Rockman Group came and conducted some student interviews to find out how their relationship with science and STEM and research and career options had changed throughout their project. And it was just great to hear their responses. They just all had a wonderful time, and I couldn't have been more delighted. This is some of the data that we had collected. I wanted to show you what it looked like. This was from the totality images before totality. Partial images before totality. And you can see two sunspots prominent in the center of the sun. And then our data, we were lucky enough to have it be used as the baseline data for not just the 20 groups that got the grant, but there were actually a total of 80 groups in the Dynamic Eclipse Broadcast Initiative. And they used our data, the two sunspots, to orient others' data and overlay the images so they were all be in the same orientation. And then this was an early processing of one of our totality images, or some of our totality images, because they would stack the rapid fire images on top of each other with the different exposures. So you're able to get not washed out corona right above the sun surface and still see all the tendrils as you go out. And then with further processing, they can get rid of some of the noise and adjust it so that you can get nice crisp images. And so Southern Illinois University is still working on those. And I just want to leave you with this image here that I love so much. And I would love to chat with you some more, answer any questions. And thank you very much for attending and listening.
Hello and welcome to my talk. My name is Elaine Hammer. I'm from Friedrich Schiller University in Jena, Germany. And today I'd like to show you how to integrate astronomy into the mathematics lessons without taking away valuable time from the math curriculum. And I'll begin by shortly telling you why I'm pursuing this approach. Here you see a map of Germany and its states, and the colors show you where and if astronomy is taught in school, in secondary school. And you only see 3 states that actually have it as a separate subject. The yellow states have it incorporated in part in the physics curriculum, and the red states don't teach anything about astronomy at all in school. Also, times change. In my state, Thuringia, the green one in the middle, just this year decided to eliminate the subject of astronomy and also incorporate it in other subjects. So there's not a lot of astronomy taught in Germany, and I'm afraid that's how it also is other countries. So I thought there's a need to teach astronomy or to convey astronomical facts and laws in some other form. And I thought, well, math is a subject that is mandatory in every grade. So in math lessons, we have word problems or applied problems anyways that need a topic and a content. And I looked at 24 math textbooks and analyzed them and found out that astronomy so far is the least used topic at all. So I wanted to add to that to help the diversity of math problems and to convey something about the universe to school kids in Germany. So the goal is to use either a fact that's like a one-sentence truth, like moon moves away every year from Earth, or data or a whole data set, or a law, so a formula in the math problems that I'm going to create. And the topics, the astronomical topics I'm using for it are the ones you see here. In the top row, that's what I would call basic knowledge, because those are the contents that we would teach if astronomy were a subject in school. And the lower row are modern topics in astronomy that I would also like to incorporate in the math problems. Today, I'm going to show you 3 examples. It's going to be a colorful mix of everything that's possible. You see these 3 problems, they come from different branches of mathematics. 2 of them will be mostly closed problem. 1 will be an open problem. I have single work, group work, partner work. So yeah, it's going to be fun to see. With the problems, I'm also creating sample solutions and a teacher's commentary. The teacher's commentary is to give more background information or to alleviate hesitation in using the problems for those teachers who are not specialized in astronomy. But today I'm only showing you examples. And for that, I'm going to switch my screens. All the examples that I'm going to show you today are for grades 5 and 6. So this is the first one, called Traveling Through Space-Times, and it's about learning how to use a coordinate system. When I create the problems, I have to think about what do the pupils know prior about the astronomical topic and what is my goal of what do I want to convey. And space-time is a very deep and heavy topic, and those kids are only like 10 years old. So I decided in the introduction to only tell them that, you know, for physicists, space and time go together, they form a unit, and we have these cool coordinate systems that tell us how objects move in space and time. So nothing about relativity or Einstein. And then they have these boxes here that explain how to read the axis. So space shows us the location in space, and time is the time passed since the moment now. And we start with, of course, from, you know, we go from easy to more difficult. So we start with an easy exercise. We just have 3 locations given, and there's no movement. It's just time passing, and the kids need to draw the points like a couple of hours later into the coordinate system. Then the next step is adding the movement, the change of space. I'm not using the word world line here. I'm just explaining to the kids that, you know, as time passes, it creates a line. And when you move your location, it also creates a line. So the exercise that goes with it, the task that goes with it is we basically have a story here. We have locations given, and we have 4 friends. They're all together in house C now, and they, you know, have different journeys, and at the end, some of them meet up, and the kids are supposed to draw it in the coordinate system. The third task, sub-problem, is an open problem, because now they know how the coordinate system works. They're supposed to write their own story, and there are again some houses and locations given. They can add as many people as they want to, and then they draw their own space-time diagram, read the story to the neighbor, and the neighbor checks if the diagram actually goes together with what the story tells. In the last subproblem, I teach them about how a point in the space-time diagram is an event, and I give them certain events, and then they have to find the events that are at the same location or at the same time or in the past or in the future of a certain event. So this is about the understanding of simultaneity of events, or things occurring at the same location, and they need to understand, like, from a certain point, where's the past of it in the diagram and where's the future of it in the diagram. The next problem is about sunspots. And I might add here, the original worksheets are not as colorful. I've added some color for you to help the presentation and for you to follow me along more easily. Here in the introduction, I tell them about what a sunspot is. It's a dark spot on the surface of the sun, and it's an indicator for the sun's activity. And the activity is important because the activity of the sun has influence on us, on the Earth. And the goal here is to give them a feeling that the sun is ever changing, because here we work with real data, the average number of sunspots per month from different months and years. And here they should get a feeling for how the numbers change. They do some statistics with it, and then they're supposed to assess, like, what statistical value is best to judge the risk of a disturbance due to solar activity. In subproblem 2 here, they get a little historical fact, because here it tells them the monthly sunspot numbers were recorded since 1749. And in the third subproblem, again, they have some daily sunspot numbers given, and they have to do some statistics with it. And this subproblem teaches them that statistics can be easily manipulated by selectively choosing specific values or just specific times when you collect the data, and that it's very important for science to gather data daily, or in general, just to gather as much data as you can. And the fourth subproblem is a group work or a task for the whole class, actually, because here they are supposed to rediscover the Schwabe cycle, so the fluctuation in the yearly numbers of sunspots. And we have a lot of data for that starting in the year 1975, so that's why it's a task for the whole class. So each pupil can calculate with like 1 year. It doesn't have to do like 50 years by himself. And I'll show you the solution. When they calculated the mean average for the year, the mean arithmetic, they will get this nice diagram. So it's 4 Schwabe cycles, and they're supposed to calculate what is the arithmetic mean of the length of such a Schwabe cycle. And so they can they just count the years from maximum to maximum and or from minimum to minimum, and then they will end up with a result of its 11.1 years, which is really funny, because it's a great coincidence, but 11.1 is actually the overall average since sunspot numbers have been recorded, and that the last 4 cycles end up with exactly that value. It's kind of lucky. The last one is a rather short one. It's an open problem, and it's about geometry. It's about the robots on Mars, the rovers. And in the introduction, I tell them about the Mars rover, its curiosity or perseverance, and what their task was on the Mars, and what they found out. For example, Curiosity found out that yes, there once was liquid water on Mars in lakes and rivers. And then this is the sheet for partner 1 with the Curiosity rover. They have this nice coloring picture here. It explains a little bit about the parts of the robots, and then they have to work with angles, types of angles, and estimate the size of angles. And I hope as they work with this sheet, they really come to appreciate the technological feat they represent, like having rovers on Mars, like gathering data on a different planet. That's quite an accomplishment for humankind, I think. So in the end, I would like to show you some feedback the pupils gave me, and I'm going to switch my screens again for that. So I took the problems that I had created and took them to schools and tried them out with pupils. All in all, I collected feedback from 185 students across grades 6 to 10. I'm only going to show you the results of the ones from grade 6 here. They've got a little form they could express their opinions on using a scale. So it was very sweet and short for kids that age. So I first asked them how much they knew about the astronomical topic before they worked on the math problem, and this is the result of it. And then I asked, how much would you say you learned, and how much do you know now more about this topic? And here you can see the result of it. And what I expected was like, yeah, of course, the people who already know a lot, they're probably here. They know nothing more, right? So it should look like this. If you already know a lot, you cannot learn a lot more. If you know nothing, you can learn a lot more by solving this problem. But the actual results looked like this. That was kind of a surprise to me. No matter how high or low your prior knowledge was, there are always students who felt like they learned a lot, and always some who felt like they didn't learn like a lot. But most of them still learned something, and there's really only a few who said like, I already knew everything. I also asked them how interesting they found the astronomical topic, and I'm very glad that the majority said, yeah, that was interesting to me. And for me personally, the most important question was, well, compared to a typical math problem from a textbook, was it more interesting? Was it better? Was it worse? And 91% stated that compared to a traditional textbook problem, the developed problems were like equally or even better. So I'm really happy about this. And it really encouraged me to go on with my project. And I would like to encourage you also to try things like this out in your country and in your schools. If you have any more questions about it, you can ask me today, and you can also write me an email to this address. Also, if you would like to receive the problems, the worksheets, then you can also write me in this address. Thank you so much for joining today.